Hello, class. This is GT 501, lecture 6, electric and hybrid electric vehicle architectures. Today, we're going to start talking about electric propulsion systems, and we're going to start that with overview on architectures first. Right. The outline is listed as follows. We're going to start with series configuration, parallel configuration, split configuration, plug-in HEV, micro hybrid. We briefly talked about this before, so I may go fast for a couple of these configurations and spend more time on things that are more difficult, okay? Architecture. Major decisions for electric vehicle designs are as shown as follows. What level of electrification do we want? What is the target level of electrification for the target vehicle that you are trying to design or produce? You need to first determine that electrification level, and then you need to determine which configuration you want to use for that level of electrification. And then once those are determined, you also need to determine component sizing to optimize the size of the components for the given target vehicle and configuration. And then finally, to actually control the powertrain in the vehicle, you need to come up with a real-time controller that can manage your fuel economy, energy, and the drivability. And we're in academia, we usually look at all of these, but from this tree, control is the last part. But when you actually want to design, investigate component sizing and configuration, if you want to compare design A with design B, you need to optimize your control so that it's a fair comparison. So, and academically, this control part is actually what makes this whole, EV design makes complicated. So, and theoretically complicated. So we're going to spend some time on controls. Levels of electrification. So we looked at this slide, and on the left side we have conventional powertrain, and then on your right side we have pure battery EV, and in between there's hybrids. There's mild hybrid, strong hybrid, plug-in hybrid, and then extended range EV. Extended range EV is also a type of plug-in hybrid, but extended EV has the pure EV capability, meaning that if your battery is fully charged, then the engine does not have to come on. On the other hand, plug-in hybrid is usually the term used for smaller or lower level of electrification, meaning that even if your battery is fully charged, if you ask for high speed, high power, your engine may have to come on, okay? You can also look at levels of electrification from size of motor and battery. So we're looking at, when we talk about micro hybrid, you're looking at, 2 to 4, but nowadays it's actually more like 4 to up to even 8. And then for mild hybrid, we are looking at 15 to 20-ish. For full hybrids, we are looking at 30 to 50 kilowatt motor. And obviously battery needs to be properly designed so that it can provide that power from the battery. And because the voltage is directly related to motor, your voltage level of the battery also needs to be increased as you go from micro to full hybrid. And fuel economy benefit of going from micro to full hybrid is that, oh, sorry about this. This number is wrong, okay? So fuel economy, we are looking at about 25 to 40 or even higher for some cases. But as you go lower with smaller, lower electrification, such as mild hybrid and micro hybrid, you are looking at lower level fuel economy improvement. So usually, 10 to say 20, 25. Micro hybrids, 5 to 10% fuel economy improvement. But of course, micro hybrids is cheaper. Full hybrids is more expensive. So you are paying for these components upfront, and you get fuel economy and you save fuels. Micro hybrids or conventional hybrids, it's cheaper, but you will have to pay a little bit more for the fuel consumption. Configurations. I shared this slide with you before. So we have series hybrid, parallel hybrid, and then split hybrid. And then there's multi-mode hybrid that uses combination of these hybrids. First, series hybrid, parallel hybrid, split hybrids. And let's take a closer look into each type of configuration. This is a quick history of series hybrid. It's not like hybrid is brand new concept in the early 20,000. It's actually quite old, and early 1900, people actually tried EVs and hybrids. Initially, series hybrid was tested, but obviously, motor, inverter, battery technology wasn't there to support this concept, right? Just like EVs. But series hybrid does have some benefits, advantages. For instance, there's no mechanical connection between the engine and the wheels. Excellent flexibility in engine operation, which leads to high efficiency. Simple drivetrain opportunity for packaging. All-wheel drive, if you like. So distributed power source. And then there's large motor, multiple energy conversions in the system. So all of these leads to either increased cost or lower efficiency, despite high efficiency coming from flexible engine operation. And this may be suitable for plug-in hybrids, fuel cell hybrids, or other special vehicles, such as these examples. They use series hybrid configuration because of these advantages we talked about. So we did already have some questions on this. So I think I already answered to that question and mentioned about these, submarine and some military vehicles, with distributed motors. And then there's space vehicle, Mars rover. They usually use series hybrid, where you need to be able to produce power from one component, and then you have many accessories and distributed traction motor. Okay. So, but because of the disadvantages, such as low efficiency, large motor, this is usually critical, especially the cost. Weight, cost, size is a critical factor for passenger vehicles. So series hybrid is usually not used for passenger vehicles. Instead, there's parallel hybrid and then split hybrids that are usually used for passenger vehicles because it requires smaller electrical components. Especially parallel hybrids use only one motor, relatively small motor, inverter and battery, because it only supports or assists your main power source, which is the engine. And you still get to use transmission, and you're placing motor between those two. So you no longer need a torque converter, which is very inefficient component. And then if you need more power, then motor and battery can provide extra power. If you need to take power, if you have excess power from the engine, the motor and the battery can take some of that power away. Okay. All right. And one of the benefit of this is this is retrofit, meaning that you just need to put motor between engine and transmission, and you can still use engine and transmission that are already existing. And that's a relatively small design change, and you still get to use existing technologies, and the control is also simpler, easier in this case. And most of all, you usually can obtain higher efficiency from this mechanical connection. But on the other hand, if you use automatic transmission, you lose some of that energy within the transmission. So in series hybrid, you did not have mechanical connection to the wheel, so your engine can operate at any operating point. So you can operate engine at best efficiency, regardless of vehicle speed and torque. But in parallel hybrid, you are still connected mechanically. So you do need transmission, because your engine is mechanically connected to wheel, so you do need transmission. So engine operation is somewhat limited. It's not completely free, but transmission gives you some freedom to operate. But because it's mechanically connected, the power transmission doesn't require this energy conversion losses where motor and generator usually suffers. So if your motor have, say, generator has 90% efficiency and motor has 90% efficiency, then even if inverter is 100% efficient, by the time you get to the wheel, you only have 81% and 20% is lost. But usually mechanical connection is 97, 98% efficient. Of course, there's transmission loss, so it's not 88 or 97 or 98. It's lower than that. And there are variations of parallel hybrids depending on where you put that motor. So this one is located between engine and transmission, and usually that's called P2 hybrid. And usually P2 hybrid is used for strong hybrid passenger vehicles. But you can also put smaller motor next to the engine, which is P1 and P0. So P1 and P0 is more suitable for micro hybrids. And then you can also put motor at the output of gearbox or at the rear wheel axle usually for rear wheel drive heavy duty vehicles. Okay. So these are some of that examples illustrated. So P0 has motor connected to the engine through the belt. P2 is has a motor that's located between the engine and the transmission. P3 is connected to the output of transmission, and then P4 is connected to the other axle of where engine and transmission is connected. So this can give you four-wheel capability if you can properly control. So let's take a look at parallel hybrids. One type of parallel hybrid configuration, which is Hyundai Sonata hybrid system. This one is, to be exact, P1, P2 system. And that's because you have two motors. There's one traction motor between engine and transmission. And then you have another small motor connected to the engine. And main reason of having this second small motor was to start the engine, because starting the engine using this traction motor and clutch was challenging. And then the system evolved from there. So, but because you have extra small motor, you can have many different modes, such as here. So not just so if you had P2 only, P2 motor only, then you would have EV and HEV mode. but because you have this extra small motor, you can actually do other modes, such as say idle charging, which can only be done in series mode. Engine cranking, like I said, this was one of the major reasons for having HSG, which this is hybrid starter generator. That's what Hyundai calls it. And there's also a series mode they can use using this HSG motor, meaning that you can decouple this and you can operate your engine and you can generate through the HSG, but HSG is small motor, so it's not really suitable for series hybrid, but you can still do that. So anyway, so this started from parallel hybrid, but it's actually closer. It's actually technically it's series parallel hybrid, because you do have this second small motor connected to the engine, which works as a generator often. So you sort of have series hybrid mode, okay? Even though it's not the most efficient mode. So that's why I think that's why they don't actually use that mode that much and do not have that mode here. Okay. And parallel there are other parallel hybrid configurations. Honda had IMA, integrated motor assist. So this was mild hybrid, where they had some small motor between engine and transmission, but their sales was not successful. It was slightly more expensive, but fuel economy was also not that impressive. And then the design of inside wasn't that attractive. So, multiple reasons made those vehicles didn't quite sell much. And then there was CVT-based, hybrids. They also use CVT and motor to improve fuel economy. But like I mentioned, I think last week, CVT is not very responsive. It doesn't give you that direct connect feel, and people didn't like that feel. So if you step on the gas, your downshift doesn't happen fast. So it slowly shifts to down gears, and that leads to sort of delay, acceleration delay. And this is what the net powertrain torque line looks like. X being engine speed, Y being torque, and you have this downsized engine. Usually you would need a bigger engine, 1.7 liter, but because you have motor, you can actually downsize, and that can help you with fuel economy. Usually smaller motor is more efficient, and but you have less torque and less power, so you need to make that up using your motor and battery. So this is the motor traction torque. Okay, so if you add them up, engine plus motor, this is what you get. Okay. And it was giving pretty good fuel economy, slightly lower than Prius. But the vehicle wasn't that attractive and didn't quite sell well. And then there's another parallel hybrid configuration from Nissan or Infinity. This is a P2 system, and they have clutch between engine and the motor, and motor is located between the engine clutch and the transmission. Nissan and Infinity, they were pushing developing this P2 hybrid for I think they were the probably first one to push hybrid as a sort of performance car, meaning that you get performance boost from having this motor rather than focusing on maximizing fuel economy. Okay, and nowadays many of the German cars are actually doing that. So both improved fuel economy plus extra power boost you can get from the motor. Okay. Oh, by the way, this Nissan P2 system does not have the small motor connected to the engine, just like the Hyundai system, and so they had to handle engine start problem using this clutch control and the motor control. So back in the old days, they had this issue of engine start problem, and it was not very pleasant to drive, and you were able to feel these engines start, and there were delays. But there's no substantial delay with P1, P2 system, because P1 can start the engine separately, separate from P2 traction motor. Okay. And then there's a recent Honda Accord hybrid system. This one is sort of P2, P3 system. So you have one motor connected to the wheel, and then you have a generator that's connected to the engine. But you have a clutch that can disconnect engine from the wheel. So the way this works is that if you disconnect clutch, now it's an EV mode. And then if you operate your engine and generate, then this becomes series hybrid. Okay. And then you can also, so this is series hybrid. Okay. And then you can also have engine drive mode. I would say this is more of a P2 hybrid, parallel hybrid, because you could drive the vehicle using only the engine, but you can also support the vehicle using the motor or the generator. So this can work as a parallel hybrid. So let me fix this. Okay, this is series hybrid, and this is parallel hybrid. And then of course there's a region mode. Okay, so this was an interesting concept because they removed transmission by having this generator. So they do not have multi-mode, multi-speed transmission. Instead, they have a generator. So this is series hybrid with mechanical connection, mechanical clutch, that can make this into a parallel hybrid, okay? But because this does not have transmission, you only have a single speed parallel mode, okay? When compared to P2, these P2 hybrid, you have parallel mode with multiple speed. So they use, so usually Honda system operates the parallel mode at high speed, where direct engine connection is helpful and good. So at high speed, usually engine is efficient. So that's how it's operated. And so please take a look at this video. I'm going to skip during the lecture, but please take a look. Should be interesting video, okay? The way this Honda hybrid system is, multi-mode, series parallel multi-mode system. And this, oh, by the way, the disadvantage of this is you do need a relatively large generator and motor. So this is more suitable for plug-in hybrid rather than just regular conventional hybrid, okay? Because you need a large motor and generator. Similar problem with series hybrid, because this is series hybrid with parallel mode, okay? But you do not need transmission, okay? And this is how Honda system operates. So usually when you start the vehicle, you operate in the EV mode. And when you're cruising at low speed, you can either charge or help the engine from the battery, so you can accelerate better when you're accelerating. And then when you're cruising at high speed, usually you can either operate in just pure EV mode, or you can drive in engine drive mode, okay? Yeah, and then there's region. And then there's split hybrid. In split hybrids, why split hybrids are popular? So there are some inherent problems with series and parallel hybrids. For serial hybrid, there's energy losses due to this mechanical to electrical and back to mechanical energy conversion losses. And then there's large component sizes, because all of the engine power has to travel through generator and the motor. And motor is the only way to propel your vehicle, and generator is the only way to generate your engine power. And with parallel hybrid, your engine speed and vehicle speed are coupled through the transmission. So this can be good and bad. So engine does not always work in the most efficient state. And then there's a large speed range electric motor needed if it's post-transmission. Back to transmission issue, because transmission is used, you have some losses from transmission. but you do not have energy conversion losses. And then you have partly limited engine speed, engine operation. Okay. The split hybrid came up with, so split hybrid was trying to address some of these issues. Okay. So meaning that split hybrid wanted to avoid some of the disadvantages of series hybrid, and that was done by using this power split device, which is this mechanical gear set, and which usually have 3 shafts coming out of the gear set, which is connected to the engine, generator, and the wheel, where motor is connected to the wheel. By the way, this is a Toyota hybrid system, but there are other types of split hybrids. But the downside, so by doing this, you actually can reduce size of the generator and the motor, because you can actually have mechanical power flow this direction, and only part of your engine power travels through the electrical path. Okay. Let's take a closer look at split hybrids. You can also look at from this view. So engine is connected to a gearing where it's connected to the final drive and generator. And then you have final drive that's connected to the gear and another electric motor. And these two electric motor is connected each other and with the battery. Okay. And if you look at if you take a closer look at the mechanism of split Toyota hybrid system, okay, this is just one type of split hybrid. And if you look, there is this planetary gear set. Okay, this is a planetary gear set. And within the planetary gear set, there's ring gear at the most outer part, and then there's sun gear, which is at the center of the gear, and then there's planet gears between the ring and sun. So planet gear is connected is connecting sun and ring gear. Okay. And so this is from the side view. And if you look at this planetary gear set, there's 3 shafts coming out. So there's planet gear. There's a carrier that's carrying planet gears, and there's a shaft coming out of that. And then there's a ring gear shaft, which is connecting motor and the final drive. And then there's there is this sun gear, okay, which is connected to the generator. So there's 3 shafts coming out of this, one gear set, and so you do need, you must have 2 shafts on one side. Okay, so in this drawing, you can see there is 1 shaft here, and there's 1 shaft. So they must be coaxial. So all 3 shafts are on the same axis, and 2 shafts of those 2 out of 3 have to be on the same side, meaning that 1 shaft has to be inside of another shaft. So it's mechanically very interesting design. Okay. And Toyota, usually Toyota and General Motors have been using split hybrid configurations, and these are some of the designs they came up with. So the point here is that there's many types of split hybrids. So Toyota hybrid is using different architecture depending on their applications, whether it's SUV, high performance vehicle, or light duty, light passenger vehicle. And then GM is also using another type of split hybrids, Volt, and then there's two mode, and so forth. And that's, if you think about it, that's very natural. Compared to parallel hybrid or series hybrid, there were not that much freedom when it comes to architecture or design. But because you have four components: engine, generator, motor, and the final gear. So you have four: engine, wheel, motor, generator, and then you can connect these four components with 3 shaft if you're using one PG, right? Sun gear, ring gear, and then carrier. So depending on how you connect them, you can generate different combinations, okay? And plus, if you start using clutches, then that introduces more multi-modes, and that introduces more complexity and bigger design space, okay? Or if you use more planetary gear sets, okay? And we'll talk more about this towards the second half of the semester, okay? So let's take a look at how Toyota system works. And this is the planetary gear set I mentioned. It's actually not that big. It's the size of a cola can. And if you look inside of the planetary gear set, you have this sun gear, and then you have planet gears, and then you have carrier that's holding planet gears, and then you have this ring gear. So you have 1, and then 2, and then 3 rotating parts, okay, shaft. And you can connect them with different components, and they can generate different designs or architectures. So here, looking at some of the early Toyota systems, here's the engine. Here is the final drive. This is the power split device, which is nothing more than planetary gear set, which is this red part. And then you have a large motor. Then you have a small motor, which is generator. And then it's, mechanically, these 4 components are mechanically connected by planetary gear sets. To explain better how planetary gear set works, this is kinematics of planetary gear sets, meaning that this is the geometrical relationship between different shafts and gear. So based on this drawing, you can derive this kinematic equations, point A, point B, and then by plugging in these equations, you can come up with this equation, which is which is a sort of constraint and kinematic equation. And usually this, because if you think about it, this planetary gear set is difficult to visualize because there's three shafts rotating at different speeds, and visualizing these, the operating principles of planetary gear set is not very clear. So to help understand how PG operates, we can employ a lever analogy. And what that does is we're going to draw a lever and represent planetary gear set using a lever. So this ring gear, this node represents ring gear, this node represents carrier, this node represents sun gear, and then x-axis is the speed of that node, okay, that gear or shaft. And what this means is that, oh, by the way, this length of this lever is number of ring gear teeth and number of sun gear teeth. So that's what determines the gear ratio between three drive shafts, and that actually determines where this carrier node will be located. It can be located here, or here, or here, right? Depending on the gear ratios. But anyway, if you use this lever, it's much easier to visualize what happens when you change speed of one or more shaft. Okay, so in this case, sun gear is faster than carrier and ring gear is the slowest. Or when this becomes something like this, your ring gear becomes fast, sun gear becomes slightly negative, and carrier is weighted sum of these two speed. Okay, and this is exactly what that means mathematically. This is, if you think about it, speed of carrier is weighted sum of sun and ring gear. Okay, so S divided by R plus S, R divided by R plus S is the weighting of each node. So the lever, this PG, has three node, meaning that it can have three different speed, and that means three degrees of freedom when it comes to equations of motion. But if you apply this kinematic constraints relationship, you are basically removing 1 degrees of freedom. And what that means is, if you determine 1 and 2 speed, then third speed is automatically determined by this kinematic equation. So this equation deletes 1 degrees of freedom. And this is also useful because you can also apply some of the torque applied to the lever, and you can visualize how the lever will behave, move as a result of applied torque. So you could, for example, if you apply 3 torque applied to the lever. Oh, by the way, you can, one confusion you can you can easily fall into is, in reality, this is torque, right? But because we used lever analogy, from this visualization point of view, it looks like a force. You should consider it as a force. It can be, okay? So this is force vector from visualization perspective, but in reality it's a torque, right? So Newton meter. Just be careful with that. Okay. So when you have these three torque applied on the on this lever, we can drive some static balance equations. If it's if it's balanced, if it's a steady state condition, then we can derive static balance equations. But if it's not steady state, meaning that if there's if omega dot is not equal to 0, then it becomes dynamic equations and a dynamic model that describes the motion of these three speeds. Okay, we'll talk more about this later on again, more in detail. But I want you to still understand the main operation concept of split hybrids. And this is another way of looking at split hybrids. So we have a motor, engine, and then we have a planetary gear, power split gearing, and that splits mechanical torque and power into two paths. And this path is mechanical path directly connected to the wheel. And then we have some mechanical power flows into the generator, and that converts that power into generator electrical power, and that's fed to the motor, and motor converts electrical power back to mechanical power and to the wheel. Okay, but remember, at steady state, this power, this power, this power should be equal, right? At steady state, this power, this power, this power should be equal, so that battery is not used and battery state of charge is constant. But if you are assisting the powertrain from the battery, or if you're taking some energy away from the battery, this power may be smaller or larger than this value. Okay. By the way, the whole point of having this complex design and control, is to use so hopefully we can have the free the engine can operate free from the wheel speed, so sort of work like a series hybrid, but still majority of the mechanical power flows through the mechanical path, so that it's more efficient than the electrical path. And then by doing so, the generator and the motor can be smaller, okay, than the series hybrid, because majority of the mechanical power is directly flowing through the mechanical path. Okay. To give you a better idea of how split total hybrid system works, this lever analogy explains that. At rest, this is at rest, and then go through launching, smooth launching, quick launching, normal driving, or close to steady state, or heavy acceleration modes are shown here. So smooth launch means EV mode. So by the way, generator is connected to sun, engine is connected to carrier, motor, tractive motor is connected to ring. So when you're slowly launching, you can use EV mode, and then your motor can accelerate your vehicle using the motor, okay, traction motor, the ring gear. So ring gear speed increases. So here is also the vehicle, okay, vehicle and motor. So motor and the vehicle speed increases, and note that generator speed decreases as a result of increased vehicle speed, because engine is not moving, omega equal to 0. But as you start driving the vehicle, or if you want, higher acceleration or quick launch, then vehicle has a low speed. So, but your engine should be turned on to, produce main tractive power. So to do that, you need to start the engine using generator first. So engine starts from 0 speed, and then as engine produces torque and power, you need to apply reaction torque or generating torque at the generator, so that your vehicle speed increases, okay? And at higher speed or steady state conditions, you want to make sure that engine power flows to the wheel, the vehicle, and want to minimize this electrical path, okay? So you want to make this small at steady state because you want to maximize efficiency. And you can do that by reducing generator speed, okay? And for heavy acceleration, you want to apply maximum torque and power from the engine, and you need some reaction torque from the generator, so that you're pushing the vehicle to higher speed, okay? And this is a visualized a video clip of a launch condition. So please. For some reason, it's not playing in my tablet. So please take a look, okay? There is like I said, there are other types of split hybrids. It's not just a Toyota hybrid system we discussed today. There's Allison hybrids from General Motors. There's dual mode split hybrids from General Motors, which uses 2 planetary gear sets and 2 clutches to be able to shift from low speed mode to high speed mode, okay? And we'll talk more about this in the second half of the semester. So don't worry about it if you do not understand these slides. It's just that there are many variations, many types of split hybrid architectures we can create using multiple PG and multiple clutches. And same applies here, same message. There are different ways of creating different split hybrids. but some are better in fuel economy. Some are better at better acceleration performance. Some are not even feasible as a vehicle powertrain. Okay. So I will stop here, and because we have national holiday, Chuseok next week, I'm going to upload one lecture video today, and then I'm going to continue with next lecture from next week, and we will not have discussion session. So we will have discussion sessions on 28th, the week after next week, and at that time we are going to take questions for 3 lectures. Okay, lecture 6, 7, and 8, and we are going to also distribute homework number 1. It's time for homework, right? So we're going to distribute homework number 1 probably tomorrow, and it'll be due, like, I don't know, maybe 10 days from tomorrow. We will make an announcement about that through KLMS or email. So please take a look at homework and see if you can solve some of the problems earlier, right away, and then you can handle some of the problems after Chuseok. Okay. All right. Thank you for your attention, and have a good long weekend. Okay. Bye-bye. Hello, class. Welcome back. GT 501, modeling and control of electric propulsion systems. Last time we didn't finish lecture 6, so I'm going to finish lecture 6 first and then move on to lecture 7. Okay. So last time we covered different architecture of electric powertrain. I believe we covered up to here. So we talked about when we design electric vehicle, we have to make decisions such as levels of electrification, configuration, component sizing, and control. And here, if you look at this outline, the first 3 is configuration or architecture. There are series configuration, parallel configuration, split configuration. It's also called, some people use terminology differently, and some people call it topology or architecture. By the way, what I wanted to mention here is that the first 3 were more of an architecture, but then these last two parts is more of a levels of electrification. So let's continue from plug-in hybrids today. Okay. Okay, plug-in hybrid. Benefits are energy cost and energy diversity, meaning that you could either use electricity and or fossil fuel, and that gives you a lot of freedom, and you don't need to feel the range anxiety which comes from relying purely on electricity, because the battery electric vehicles tend to have limited range and takes time to recharge, and sometimes you may not be able to find charging stations, and that's where plug-in hybrid shines. In fact, plug-in hybrid came up from the idea of, we don't really travel long distance every day, right? For instance, if you look at this figure here, x-axis is travel distance per day, and y is ratio, meaning that how many people of the population travels the x-axis distance. So for instance, in the case of Japan, if you pick, I don't know, 40 kilometer, then almost 87%, 87% of people are traveling less than 40 kilometer per day. And if you look at United States, where people tend to travel longer distance, in larger country, they tend to travel, so 60% of populations are traveling less than 40 kilometers per day. So that's, you need longer, or to give you same ratio, you need longer distance. Okay, so the idea came from this, where you don't really travel long distance every day. Then why do we need large, heavy, and expensive battery for EVs, right? Well, why don't we put smaller battery and put engine if you have to travel long distance? That way you don't have to feel this range anxiety, and then you also can rely on electricity as a main energy source, because at the usually what you would use your passenger vehicle would be commuting purposes. Many people use their vehicles as a commuting transportation mode. So as long as you're traveling short distance, you can charge and travel, commute in EV mode, and then you don't have to consume, fossil fuels, right? But when you have to travel long distance, you can start running your engine, and just works just like a conventional hybrid, right? So plug-in hybrid has that nice combination of hybrid and plug-in EV. Okay. There are two concepts of plug-in hybrids. One is a blended type, The other one is extended range EV type or CDCS type. And that's because that's usually coming from the level of electrification, meaning that if you have, larger motor and battery, then if your battery is fully charged, when I say larger, usually that means power, okay, here, in this case. And if you have enough power from motor and the battery, then if your battery is charged, then you can operate as an EV, which is this case, charge depleting mode. And then once you deplete your charge, then you can operate it as a charge sustaining mode, okay? But if you have smaller motor and battery power, then if you're traveling at higher speed, or if you step on the gas asking for high power, then engine has to come on because your motor and battery cannot provide all that power. So engine has to come on even if the battery is fully charged. And that type of plug-in hybrid is called blended type. And many of the parallel configuration-based parallel architecture is usually blended type, because you would need large. You already have transmission, and then you also will need large motor and battery. So you usually keep it small for parallel configuration. But for some architectures, such as GM Volt and Toyota Prius, which is split type, multi-mode split type architecture, they are more suitable for EREV plug-in hybrids or EREV type. And that's because these split type architecture has two motors anyways. So if you use these generator and motor as motor in EV mode, which is sometimes called two motor EV mode, then you can provide higher power. So you can work as a pure EV. So by the way, Toyota Prius is now moved to this EREV approach, and usually now Korean and Europe OEMs manufacture these blended type plug-in hybrids because Korean and Europe OEMs use parallel architecture, whereas Prius and GM Volt architecture uses two motor or multi-mode split type architecture. So it can readily provide that high EV power. For example, this is Chevy Volt configuration. This is the first generation Chevy Volt, which I think is like 10 years old or more. They came up with this idea of EREV, meaning that using this generator as a motor, it can provide two-motor EV, and it can provide both series hybrid and split output split hybrid mode. So if you look at this table, there are a total of 4 operating modes, 2 EV mode and 2 hybrid modes. So 2 EV modes consist of low speed 1-motor EV mode and high speed 2-motor EV mode. And hybrid mode, which is here noted at extended range mode, is consists of 2 modes, one being series mode and the other one being split mode. So this one is this is more suitable for high speed. This is more suitable for low speed, okay? And this is the patents they filed for first generation Voltec. They use planetary gear sets, and they connect final drive to the carrier, and then they connect one motor to the ring. Actually, I think it's sun, and then this one is ring gear. And you have 3 clutches to create different modes. So if you did not have any clutch, this would be a single mode. And if you connect C2 and C3, it becomes output split mode. And this is different from the Toyota Prius architecture, which is the input split mode. I'm going to talk more about that towards the second half of the semester. But the point here is that this is multi-mode architecture using 3 clutches. So by engaging and disengaging this clutch, you can connect different shafts, and you can disconnect or connect this power flow. And by doing that, you can generate different architecture. So that's how you can get these 4 modes, 2 EV modes and 2 hybrid modes. Okay. So this was very brilliant idea. And if you look, let's closer look at each mode. So for low speed 1-motor EV mode, you just need to engage this brake. This is ground. This is a grounding node. So your casing of the transmission. So which means the ring gear is not moving at all. Okay, and in that case, the planetary gear set works as a simple gear, fixed gear ratio, and that gives you 1-motor low-speed EV mode. And next, you can, as vehicle speed increases, if you release C1, clutch 1, and engage clutch 2, then you get this 2-motor high-speed EV mode, because now you can utilize this second motor to push the vehicle. Okay, and then for hybrid modes, one motor, so low speed series hybrid mode requires these C1 and C3 engaged, and then C2 disengaged. That way, you are mechanically decoupling the engine and generator from the drive line. So it's a series mode. So generator is generating electric power, and you have this traction motor driving the vehicle using electric power. So this is a series mode. And then if you move towards, if you look at this high-speed hybrid mode, then you need C2 and C3 engaged and C1 disengaged. And this gives you this unique output split mode, which is different from Toyota Prius input split mode. You can visit YouTube and type in, Voltec, and you should be able to find more explanations on how their powertrain operates. Okay. So I just talked about plug-in hybrid concepts, and for plug-in hybrids, I mentioned that there are two different approaches: blended type and then ER-EV type. But this is this Prius architecture is old architecture, because and they do not have this multi-mode two-motor EV mode. So you can think of this as a blended type. But the point here in this slide is that for split configuration, we can have different configurations. For instance, both Prius and Volt uses a single planetary gear set, but they have different connections between the PG and the component. So there are 4 components: engine, motor, generator, and the vehicle, the wheel. So there are 4 components, and if we use one planetary gear set, you have 3 shafts coming out of one PG. So ring gear, sun gear, and carrier, planet carrier. So, and in the case of Volt, ring gear is connected to generator and engine, and sun gear is connected to main traction motor, and carrier is connected to output wheel. In the case of Prius, ring gear is connected with traction motor, main traction motor, and sun gear with generator, and carrier with engine. And ring gear is also connected with output wheels. So they have different connections, and that leads to different characteristics and operations and performance. Another difference between these two architectures is that the Volt architecture has clutches, so you can generate different mode and different architecture. So output split mode is just one mode out of the 4 modes available for Voltec architecture, whereas this conventional hybrid Prius architecture is a single mode and do not have any clutches. But recently, I mean, a few years ago, Prius also launched, two-motor EV mode plug-in hybrids, so that they do not have to. So they wanted to move from blended type to ER-EV type, so that if battery is fully charged, engine does not have to come on. Okay. Oh, by the way, what I meant by there are still opportunities is that we are just looking at two examples of how to connect 4 components with 3 shaft, right? But if you enumerate, if you list all the combinations, actually there are 24 ways of connecting 4 components with 3 shaft. So this is a lever, right? And then we have motor 1, 2, engine, and the wheel. So we have 4 components and connect that with ring, sun, and carrier. And we have 24 input split configurations, and another 12 and 12 input and 12 output split. And you can see that Prius is right here and Volt is right here. But again, Volt is multi-mode. So output split mode is one of the 4 modes, okay? Oh, by the way, the Voltac moved on to compound split, which I'm going to talk about that later on, okay? Finally, mild hybrid is literally, it's a mild hybrid, or sometimes it's called micro hybrid, where you use minimal electric component and power. So, and for low power electrifications or hybrids, you could use 48 volt or lower, sometimes 12 volt, but usually 48 volt is now becoming a standard for these micro or mild hybrids. Okay. The main benefit of using 48 volt is that below 60 volts, there is no safety concern from electric shock or something like that. So to avoid electric shock, usually you have to use more expensive and heavy cables if you are using high voltage. But for low voltage applications, you can use much cheaper and lighter cables. So for low electrified vehicles, reducing cost is very important. So usually 48 volt is a standard in the market. Okay. So this is it for finishing the lecture 6, and let's move on to lecture 7.